Hello students, in this video I'm going to solve two second order differential equations. I'm going to go through rather quickly. I'm going to show you the basics of what to do when you have a complex number for the solution to your characteristic equation. So these both are examples of cases where we get a complex number for the roots to our characteristic equation. Now, I'm not going to go through the verification of the formula that I'm going to apply here. I have another video where I give the verification and justification through a specific example of how to apply Euler's formula to the case where you get a complex root to the characteristic equation. In this video, I'm just simply going to show you, what to do when you see that complex number and how to just formulate your solution. So I do have another video where I go through the verification, and I suggest that you take a look at that if you're wondering, like, where did this formula come from and why did I do that. Okay, so this is just a practical example of how to solve these two cases. All right, first thing we're going to do is write the characteristic equation for this ODE here on the left. So sometimes this actually turns out to be one of the more difficult steps. Students forget to align the exponent with the order of the derivative. So I have a double primed here, I'm going to get an r squared. I have a single primed here, I'm going to get r to the 1. I have a 0 prime here, so I'm going to get r to the 0, which is 1. Without this 41x term, you wouldn't have this number here, and you just have something like this, r squared minus 10r. Okay, so just remember to match up your exponents and your primes, okay, the orders, your exponents and the orders of your derivatives. So I'm just going to apply the quadratic formula to solving this quadratic equation now. So this becomes an algebra problem. 100 minus 164 is minus 64. The square root of minus 64 is 8 times the square root of minus 1. The square root of minus 1 is I. 8 divided by 2 is 4. 10 divided by 2 is 5. So I get 5 plus or minus 4i. So I get the conjugate pair here, plus or minus 4i. 5 plus or minus 4i, sorry. So I have a real part and an imaginary part associated with the imaginary number square root of minus 1. Now, remember that when you have a complex number, remember what happened to the real part. This, the exponential of this, we had a sum of the exponents, so we factored out the real part. And then the imaginary part, we used Euler's formula, and we just plugged this into the cosine and the sine term. So we got something that looked like this here. So here we'd get e to the 5t for the real part, c1 cosine, the imaginary part, 4t. What happened to the plus or minus? Well, remember, cosine is finds that the minus sign is irrelevant, is an even function. So the cosine of a negative argument is just going to be the cosine of positive. It's an even function. Plus c2 sine, and then remember the plus or minus, we just absorb that, the minus sign that we get when we have the sign of a negative argument, that's the negative sign of the positive argument, we just put that into this arbitrary constant. So this stuff in the parentheses is the result of Euler's formula for a complex exponential. And this is your solution. So when you see the real part and imaginary part, it's e to the 5t, and then multiplied by this combination of cosines and sines. That's the real form of your solution. Now, what do you do when you have 3x double prime plus 15x equals 0? Well, I'm going to factor out the 3 and divide that out. And I'll have x double prime plus 5x equals 0. So I'm going to write my characteristic equation here. Now, once again, as I said, be careful, as I mentioned in the first case. You are going to match up your order of your derivative 2 with your exponent. So that would be r squared. The order here is 0. This is the 0th derivative. That's not a prime. It's not a 1. It's a 0th derivative. You're not taking a derivative. So that's going to be r to the 0, and that's 1. So you have r squared plus 5 equals 0. You could solve this a couple different ways. You could still plug this into the quadratic formula. Since there's no r term, right, the b is 0. and the square root of minus 20 is you get a 5 times 4, so the 4 factors out, and you get a 2. 2 divided by 2 is 1, but you had a minus 5 in there, so the square root of minus 5 is square root of 5i. Don't forget the plus or minus. Likewise, you can push the 5 over to the right side by subtracting 5 from both sides. Take the square root, don't forget the plus or minus, and you get a plus or minus square root of minus 5, but that's plus or minus I square root of 5. All right. The next step then is, now that you have your roots, they're imaginary. This exponential, for example, in this case, the real part was 5. In this case, the real part is 0. So e to the 0t in this case is just going to be 1. So we won't have an exponential term in this solution. The imaginary part is I square root of 5. So we're going to take that square root of 5, and we're going to plug that into our sines and cosines. So the e to the 0t, that's a 1 sitting out here in front. Okay, so it's there, it's just the number 1. And I just take the imaginary part, I take the square root of 5, and I just use Euler's formula, and I get the cosine square root of 5t, and here I get the sine square root of 5t. Now, don't forget, these solutions are functions of t. T is the independent variable in both cases, and x is the dependent variable. X depends upon t. Why did I pick t? Because I already used an x as my dependent variable, so I want to have notation like x of x. I could have used another, I could have used s, for example, but t is conventionally the variable that's used when x, for example, is already being used, or if you want the independent variable to signify time. All right, good luck.